In this video, I'll be taking you through determination of average reservoir pressure. And determination of average reservoir pressure is important because this pressure is required in many reservoir engineering calculations such as material balance studies, water influx calculations, analysis of pressure maintenance projects, and assessing degree of reservoir continuity. And since making future predictions of production is a function of the reservoir pressure, determination of average reservoir pressure is important so that predicted pressures can be compared to actual pressures and necessary adjustments can be made. So what I'll do in this video is to take us through different methods which can be used in estimating the average reservoir pressure. And the first is determination of average reservoir pressure from the Horner plot. So there are basically two scenarios. So there's the scenario where you in which you have it's a new reservoir, a single well producing, all others shutting, and there's negligible pressure depletion. In this case, if that producing well is shutting, and is shutting for an infinite shutting time, the pressure buildup data will the straight line Horner plot will eventually extrapolate to the initial reservoir pressure. And I think that is quite easy to conceptualize. If you take a look at equation B1, if delta T becomes so large that Tp plus delta T approximates delta T, and delta T over delta T is 1, log 1 to base 10 would be 0, and the shut-in pressure would equal the initial reservoir pressure. However, there is a second scenario, and which is more prevalent, where your reservoir is finite in size. You're not assuming an infinite reservoir size. It's finite in size, and so as soon as production begins, underground withdrawal would cause pressure decline everywhere in the reservoir. Under this scenario, if you shut in the well and you allow pressure to build up, it will not, your Horner straight line plot will not extrapolate to the initial pressure. Rather, it would extrapolate to a pressure which we refer to as P star. And P star it's a force pressure. It's of it's of use for calculating the average reservoir pressure. But take note, P star would only be equal to Pi in a new reservoir where you have negligible pressure depletion. But for finite reservoirs, P star does not equate to Pi. So the pressure extrapolated to infinite shutting time, that's P star, and you can see it from here. The infinite shutting time is when Tp plus delta T over delta T equates to 1, and which we would see from here, that's this pressure. And so this pressure, P star, has no physical meaning, but it is used to determine the average reservoir pressure. Let me reiterate again, P star would only be equal to the original reservoir pressure in a newly drilled well in a green field. So for finite reservoirs, instead of Pi, which we had in equation B1, we have the shorting pressure being equal to P star plus the difference of the product of the slope to the Horner plot times the log of Horner time. Now, the observed reservoir pressure is dependent on three factors: the shape and the geometry of the drainage area, which the well investigates. 2, the position of the well relative to drainage boundaries. And 3, the length of the producing time before shorting. So the behavior of the pressure or pressure behavior as would be inferred from the test well at the end of the transient flow period would be a function of the shape and geometry of the test well drainage area, the position of the well relative to drainage boundaries, and the length of the drainage time. That's for how long the well has been producing prior to shorting. So ideally, what we should do is to solve the divisibility equation and impose the boundary conditions of pseudo steady state, and then plot. So what is done, and then solutions are plotted in dimensionless form to give the theoretical pressure buildup. So of course, we won't be going through the rigorous solutions. We'll just be applying them, and then you see that in some subsequent slides. So there are several methods I think I've mentioned using the Horner plot, which is actually the MBH method. You have the Ramy-Cobb method, the MDH method, the Darts method, Harari or direct method. You have Muscat, and you would also see that average reservoir pressure can be obtained from flow tests. That's how I'll end the video. The MDH and the MBH methods should give approximately the same value for a circular bounded reservoir, of course, with the well centrally placed. The difference, or where they differ, is that the MDH method assumes that the reservoir is in steady state prior to shorting, while the MBH does not. And this will be reiterated later that the Muscat method should be used for late time analysis. So let's start with the MBH method. So the MBH method entails using the Horner plots. So for the MBH method, the authors found out that the average pressure So the authors of the MBH method found out that the average reservoir pressure can be related to P star if the geometry, shape and location of the well relative to the boundaries are known. So they developed a set of correction charts for various drainage geometries. I'll show that in shortly. And the Y values of these figures represent the MBH dimensionless pressure. And the final equation is actually what you have here, with a linear relationship between the average pressure, average reservoir pressure, and the MBH pressure. The MBH dimensionless pressure is determined as a function of the dimensionless producing time, which corresponds to the flowing time. And that's what you have in this equation. And in the next slide, I will illustrate the use of these equations. Okay, so I'll walk you through the steps for the procedure for the MBH method. So using the MBH method requires one, producing the Horner plot, two, extrapolating the semi-log straight line to the value of P star, and this is where the point at which the Horner time is equal to 1, obtaining the slope, and then we need to calculate the dimensionless producing time as a function of the producing time, that's here. And then we need to find the closest approximation to the shape of the well drainage area and the correction curves, and identify the appropriate correction curve. The sixth step requires reading of the dimensionless MBH pressure as a function of the dimensionless producing time, and then applying the equation I've shown before to obtain the average reservoir pressure. Now, it's noteworthy that it's usually recommended that the producing time should be compared with the time required to reach pseudo-steady state. If the producing time is way larger than the time required to reach pseudo-steady state, the time to reach pseudo-steady state should replace TP in this equation, and that will be used in calculating the average reservoir pressure. So let me take, so this is the charts for different reservoir geometries for obtaining the dimensionless MBH pressure, and it's used shortly. So I think it's best understood with an example. And this is an example which we've used in previous lectures. So table B1 to the left shows the pressure buildup data from an oil well with an estimated drainage radius of 2,640 feet. Before shutting, the well had produced at a stabilized rate of 4,900 stock ton barrels per day for 310 hours. So below is the known reservoir data. We're asked to calculate the average pressure in the well drainage area and also the corresponding drainage area. And I think it's, so let's get into it. So remember that the first step is to produce the Horner plot, which I have done here. And of course, you know, the Horner plot entails plotting the short-in bottom hole pressure against the Horner time. And remember, as I said in an earlier, in the last lecture, the scale here for the x-axis is reversed so that this would give the build-up, expected build-up straight line, at least under infinite acting radial flow. So what is done is this, the straight line portion, of course, this is the portion affected by well-bore effects. And then you see that there's a departure from the straight line. And at this point, of course, boundary effects begin to set in. But the straight line portion is extrapolated to Tp plus delta T divided by delta T is equal to 1. So this is the P star value, in this case 3365. One significant pressure is the pressure at P1 hour. But remember, in this case, P1 hour implies that delta T is equal to 1. So P1 hour is obtained from Tp plus 1 over 1. So at that pressure, that's Tp in our case is 310. 310 plus 1 is 311. So this is 100, 200, 300, 300, and so that's why it's obtained from here. The slope of this plot is obtained from any of the cycles, and that was treated in the last lecture. In this case, it's 40 psi per cycle. So I've shown the extrapolation of the Horner straight line to give P star, and then everyone knows how the slope of the straight line is obtained. The next thing is to compare the producing time required to reach to the steady state to the producing time. Know that the producing time is given, that's 310 hours. The time to reach to the steady state was shown in an earlier slide. This is the porosity. It actually looks like an inverse of this equation. This is porosity, viscosity, and this is compressibility factor. This is RE, and then A, this is the permeability as obtained from the Horner's plot. In this case, time to reach to the steady state is obtained at 263 hours. If you compare that, this is taken to dimensionless form, but you see that TPSS is less than TP. So from what we saw on the other slide, one should be able to replace TP with TPSS. But if you see in dimensionless form, you see that they are quite close. So we go on using, with TP. So you've seen here, this is So the MBH dimensionless producing time, TPDA, is obtained with this. So using this to obtain your TPDA, that's the dimensionless producing time, this value is now used to enter into figure B6, and figure B6, I think I'd flag that that's here. So I think the value obtained then was 0.1117. This is 1 and this is 0.1. So you're entering at somewhere here. So the next thing is, which of these do you use? We're looking at the hexagon circle square, that's this. And then you read off the corresponding dimensionless MBH pressure. So, and this would give you a value of 1.34, and substituting 1.34 into the equation for the average reservoir pressure would give you the 3342. So P star is obtained from the extrapolation of the Horner plot. Modulus M, that's the slope of the Horner plot. This is a constant. And then the dimensionless MBH pressure is what you obtain from figure B6. For this one, it's read off from the curve for the cycle. So we obtain the average reservoir pressure as 3342 psig in this case. We're also required to obtain the drainage area. So to do this, the slope of the, I think this formula, we used it, I think, towards the end of the analysis of the drawdown, the lecture for the analysis of drawdown data. It helps us get MPSS. MPSS is the slope of the Cartesian plot of pressure against time. So using this formula entails obtaining picking 3 points along the straight line portion of the Horner's plot. So I pick 3 points, Ti of course. So I picked 3 points on the Horner's plot. So for each point, you get the corresponding time and pressure. And substituting into this formula gives 0.5233 psi per hour. And this can now be substituted into the formula for obtaining well drainage area. And you see that the other parameters are given in the question. So it's just the MPSS that is obtained. And this gives